Okay. Realize I made a terrible mistake because I now realize that I didn't schedule a review on in my calendar next Tuesday. So I'm gonna have to work something out with my TA to be able to do that. Yeah, that's why you guys asked me last time. I didn't realize that it wasn't scheduled. But we'll work it out. Okay, so today we're gonna wrap up.
Dr. Denard, does that mean that the review is going to be moved from Tuesday, or does that just mean that Alex doesn't know he's doing a review?
Oh, he knows. I think the issue is whether or not he's gonna do only half of the lecture, or is it gonna have a Monday one. So I'm gonna talk to him after class because I just realized this about an hour ago. I'm gonna talk to him after class, see if he can schedule one for Monday, and also do some of it on Tuesday during class. So the idea is the lecture will be an hour and the review is gonna be an hour. That's what I'm planning. Yes.
You have a quiz scheduled for Tuesday as well.
Yes, it is.
So that I guess would cut into that time as well.
Well, I'll just do the lecture for 45 minutes. But
okay,
like I said, I'll figure it out. Yeah, we'll plan it out. It'll work just fine.
I do have a quick question.
Mm-hmm.
So next week seems to be a fairly busy week in terms of this class. And I guess the best way to phrase this is I was hoping to get like your rationale for the quiz on Tuesday being on that's going to test chapters 4 and 5, or homeworks 4 and 5. But then we have a test on Thursday, which I'm assuming will also cover those sections.
Well, I'll give you a choice. The choice is we cancel the quiz and your exam is harder, or you have the quiz and the exam is easier.
I mean, I'd like an easier exam. I was just wondering.
I mean, I can make it. But you guys asked for this because the quiz was going to be today. But you asked that it should be on the same day that the homework is due. So we did that. So,
Yeah, I mean, I wasn't trying to say change anything. I was just trying to understand.
Yeah, well, that's what to answer your question, there wasn't really a rationale. It was just the fact that there has to be a quiz, and it was supposed to be today, but it's next Tuesday. That's really what happened. I wasn't really thinking through it. You guys asked that it was moved to the same day of homework, so I did.
Okay.
Yeah, I wasn't thinking of yeah, and yeah, because my plan when I I thought about this yesterday or so, and I figured, well, maybe the quiz will test you on some things and the exam will test you on other things, and then at least not different things, but slightly differently worded, because the exam, the second exam is noticeably harder than the first one, and I'm sure you can appreciate that, not just from because I mean it, because I'm meaning to make it hard, but actually because the material is harder. So yeah, so we'll have a short quiz Tuesday, something that you can also like get right, and then the exam will be compensating for the rest of it, I guess. Yeah, it'll work out fine. But the way things are going, I think it's going well, but we might not be able to cover the very last topic, which is external mass transfer. But that's okay. We might not be able to get there, but we'll try. We'll try our best. Yeah, so we're gonna wrap up nonlinear regression. We're gonna wrap up chapter 7 or chapter, is it 6? 6. We're gonna talk a little bit about nonlinear regression, and I'm not going to spend a lot of time on that because that is something that you often now can use, Excel and MATLAB or Python or GraphPad or Kaleidograph. So the goal in linear regression is to minimize the sum of deviations and these are deviations from or differences between the measured data, right? So, and a calculated data. So calculated data meaning you'd be guessing the parameters and you'd calculate what the concentrations could be from that. So use an example is something like, okay, let's say you have concentration, say it's like 5, 10, this would be, let's say, millimolar, 100, 200. And then your measured rate. So this rate could be something you computed using one of those differentiation methods that we talked about last time. Let's say you get a measured rate. And you guess, so the first thing you would do, you would guess the form of the rate expression. So let's say you would to do that. Let's say this rate expression is, let's say you guess it to be like some Kc alpha, some power law. Then you would guess alpha. And you would calculate. So it would be, this is measured. This is calculated. Right? So you'd calculate. So I'll call it RA calc. And you would get some number that would be either close or really far off, right? Then you take what you do is you look at the deviation, which is, we'll call it S squared to N of, let's say, concentration that is measured or calculated. Or let's say, yeah, what you measured minus what you've calculated squared. That's one way you can look at the sum of the errors. So this is essentially the same idea of looking at the sum of the errors. Or you can look at fractional deviations. This is another way, looking at fractional deviations, where you measured, calculated, divided by calculated, squared. This is just fraction deviation. So you could put, you can put your deviations here. These are your errors or deviations. You can sum them up, all of those. So if you do this in Excel, you can sum up all the errors. Then you can go into Solver and tell Solver minimize. This is S squared right there. You tell Solver to minimize S squared by changing, let's say, alpha. So alpha would be in a cell right there. It would be some number. And then you would minimize it by changing alpha. So if none of you have used, some of you have not used Solver to do this, I can quickly show you an example that I worked out in Excel. So I'll share my screen of the Excel spreadsheet. Where are you? Let's see. So I'm gonna go through it in a moment, and you'll see that it's pretty straightforward.
Wait, can you bring the notes back up to copy for a second?
Okay, notes. Notes are here.
Thank you.
So now let's see if we share the other screen. This is the Excel spreadsheet. So let me go over here. So this is a batch reactor problem. What did I do here? Oh no, let's look at this problem first. Sorry. So this is an enzyme reaction problem. So S goes to P enzyme reaction, and you have a bunch of substrate concentrations. And if you remember correctly, let's say we guess a Michaelis-Menten equation. So Michaelis-Menten is Rs is equal to, we'll do minus Rs, okay, is equal to, oh, I guess I have to do something else. So let's see, minus Rs is equal to Vmax times S divided by Km plus S, right? So that's the form. We guessed that form, and we guessed some values of Vmax and Km. Okay, so we have this data. This is the data that we've collected. Okay, so we take that, and then we can use our guesses. Now I've already done solver, so I'm gonna change this to, let's say, 0.2. I'm gonna change this to 50. Okay, so I get some calculated values. You can see this is basically using the Michaelis-Menten curve. This is Vmax times some concentration of substrate over Km plus substrate gives you a calculated value. And I can basically calculate the value for each. You can see that pretty much they're pretty far off from one another. And then these are the sum of the errors. I just did some of the errors, not fractional deviations. I just did the deviations themselves. So this is calculated or measured minus calculated squared. And I can sum them all up and I get a sum of those fractions. So these are the, or some of the deviations. I meant to put some of the deviations. So you can see, now, if I go into solver, so if I go into solver, that's under data. I go into solver and I tell solver to minimize cell L21. So this is the sum of the errors. So minimize the sum of the errors. So don't put value of 0 because it's never going to reach that. So minimize the sum of the errors by changing those two cells. So we're changing O2 and O3. Change those two cells, and these are the real values, and tell Excel to change those two cells by minimizing the sum of errors. If you click solve, you can put some constraints there. You can tell it Km has to be positive, or Vmax has to be positive, or something like that. You can put those in there, but in this case, you don't need them. So if we click solve, it's going to go through, and it's going to tell you it found a solution. And you can see what the solution that it found. So you can basically keep that solution, and that gives you this curve. So this is the rate in the y-axis and the concentration on the x-axis. If we remove some data points, let's do that. Okay, let's remove some data points. You can see it tells you that Km is about 40. So this is the concentration at which you get half of the maximum rate. So the maximum rate should be about 0.5. You can see the Km is at 40. The rate there is 0.25, and the maximum rate is about 0.5. So this is saturating at that condition right there. So you can see what it looks like. This is a typical enzyme kinetic analysis. Normally, when you do experiments, you're gonna do your calculation, your measurements 3 times. So you'll have some errors in the measurements when you do those. And these are accounted for to get your to make to make a tighter curve. So for especially at those low concentrations, there could be lots of errors introduced at those low concentrations. So that could throw off your Km drastically if you don't do it right. So you could do a Lineweaver-Burk plot by linearizing. You could linearize this equation by taking the inverse of this equation. So you'd get 1 over S and 1 over R. So you could plot this essentially the same way. This is a Lineweaver-Burk plot, and we've kind of looked at it maybe a lecture ago, maybe 2. So if the slope of this curve is actually, I believe it's Vmax over Km, if I'm not mistaken, or Km over Vmax. So the slope of this curve is Km over Vmax, and the intersect is very close to 0, but it's not. The intersect here is actually, you can get the Vmax from the intersect, 1 over Vmax. All right, so, but one thing you can notice here is that the highest point over there is actually the lowest concentration. So you have to keep that in mind. So everything is inversed. So you see there's a gap, there's a pretty big gap between, concentration of, inverse concentration of 0.5 and 0.2, something like that, 0.5 and 0.25. There's a big gap here. That actually means that there is a big chance for the errors to be introduced, so that it could impact the slope quite a bit. So this is one of the downsides of doing linear regression on enzyme kinetics, is that the points that are closest to Km or that are lowest tend to have a pretty big spread in terms of their inverse concentration results. So that can introduce errors in this region pretty easily. For example, if for example, instead of 42, you had another one where it was 50, another one where it was 30, let's say 36, you'd have a pretty large error. So that could affect your Km if you take the average and the standard deviation between the 3 points. So it's something to keep in mind. That's why often linear regression can end up working quite well to minimize those errors that you would find in this lower region. All right, so yeah, so that's essentially, well, that's one way you could use regression analysis to look at differentiated data. So differentiated data meaning you have concentration versus rate. On the left here is actually concentration versus time. And then we'll get to that right in a moment. How do we go about doing regression on that? Yeah, once again, I will post these. I should have posted the one last time, but I will basically post this after class today, so you can see them. Now, if you just looked at doing linear regression on differentiated data. So this is looking at enzyme reaction. You plot it and you use Solver in Excel. But there are other softwares that actually do it even better job, like Kaleidograph and others, or Origin Lab. Now we can look at, so to summarize, if you're applying nonlinear regression to differentiated data, which is concentration versus rate, I'll just put C instead of CA. I have to get used to not doing that. Then the first thing you do, you can hypothesize what the rate equation, what you think it's going to look like. And at the very end of class, not the very end, like right after, in a few minutes, we'll talk about this hypothesizing and the other statistical methods you can use to look at your, to judge your hypothesis. You can then guess parameter values, which is what we did. And the third step is to calculate your deviations. From measured data. And then and once you do that, you can minimize those deviations. Here we use Solver in Excel. So that's how you would use nonlinear regression with differentiated data. And here we just show an example where we used it on enzyme data with the form of the Maculus-Menten. Now you can imagine if there is an inhibitor, there's is substrate inhibition, the data is going to look different. So you can think of, if you differentiate it, if you've guessed that there's an inhibitor, you set up your experiments to check for the Ki, the inhibitor constant, and you could also derive the inhibitor constant or from your experiments. Okay, so now we're going to look at if we apply nonlinear regression to integrated data, so using the integral method. So, and this is the last bit we'll be doing, and then we'll wrap up, give a conclusion here. If we do this to the integral method, now we have to go, and I don't remember if we did this last time, but the integral method is concentration versus time or space-time, depending on what reactor you use. So if you use a batch reactor, you start from some concentration and you look at it over time, so it gives you data, and you use that data to try and figure out what the rates of your what are the parameters from your rate expression. So assume, let's say you assume you've gotten data and you assume a power law rate. We've seen before that with the differential method, if you had a rate versus concentration, you could linearize this using natural log. But if you have time versus concentration, and you have a good guess this is a power law, you can go ahead and put this in a design equation. So using the mole balance for a batch reactor. So if this happened in a batch reactor, so you'd have your dCA dt equals minus K Ca alpha. And at time 0, Ca is equal to Ca naught. Okay, so these are your initial conditions. And you can actually solve for Ca, integrate and solve for Ca, and you'll find this expression here. And that works if alpha is not 1. So if alpha is not 1, you can actually differentiate the power law, and it looks like this. And you can solve for Ca doing a couple of manipulations. You can solve for Ca where it's going to be this minus to the power of 1 over 1 minus alpha. So this is your integrated power law with your initial conditions. And here you can look at the sum of your errors between. So you would use this to calculate. So you'd use to calculate CAs or RAs, I guess, or CAs. Yeah, sorry, you calculate CAs and compare to CA measured. Yeah, so you have time. You can also solve for time here. That's another way you could do it instead of solving for CA. So this is the same as saying now you have CA measured minus this CA calculated. Squared. So you can basically look at that difference. And this is KTI. This is for every I. So this is the, yeah, and this is MI. Okay, and this is I equals 1 to n. So these are the number of data points. So for each data point, you can calculate the difference and you can sum them all up. It's the same thing. And this works well for a power law. Now, if this is not a power law, the integration of, say, a Langmuir intro with kinetics with respect to, well, that's not actually very easy to do unless your data allows you to do it. But this is something that you may not be able to do with a more complicated rate expression, this sort of integration. Now, I can then now share the Excel spreadsheet and show you more or less how this is used, but it's the same idea. So if you were to go now into Excel, oh, I think am I sharing the right thing? Make sure I am. Oh, maybe I am. Okay, I wasn't sure. Yeah, now if you were to share your sharing the Excel spreadsheet, so this is a reaction where you have, I suppose I meant to say A goes to B instead of A plus B goes to C plus D. That must have been a copy mistake because there is no B in the measurement. So that's a copy and paste mistake that I made from somewhere else. Okay, and this would be CB. Okay, yeah, that was a copy mistake I made from somewhere else. So, oh. Hold on, did I mess up here? I guess we don't need this data point. Okay, so that's what's happening here. Maybe we don't even need this one because we have time and CAs, so we don't need this one because I took this from last spring and I feel like I forgot to change it, but it's okay. So we have time data and we have measured CA data, and we assume that this is a power law, which means that we can calculate using the formula we just derived. So this is the formula we just derived, calculating CA assuming that the rate is a power law. And this is just that with K and gamma. I call it gamma instead of alpha. So K and gamma are guessed to be a certain value. So maybe we can put something close. I'm not sure how close I am. Let's do that. Okay. Let's say we do that. And we look at the absolute deviations. So this is an example where we, just like before, we looked at the absolute deviations and we sum them up just like before. And we will basically use solver to ask, can we in fact minimize this guy by changing these two? And we're gonna add a constraint that K is positive. We're gonna add a constraint that this is a positive number. Let's see if that works. Oh, click OK. Oh no, I guess I have to put cancel. Okay, there we go. Let's see if that works. I can't remember if let's see if that solves. Oh, that did not go well. Okay, let's try one more time here, because I think in this example I went too far. Might have gone too far off, and sometimes it can crash. Or maybe my constraint was not a good one. Let's find out again. Ah, there we go. Now it works again. Okay. Because sometimes it could fail if you're too far out and solver just goes the other direction. So you can see that it minimized the errors to something like 110 to the minus 7, and it gives you two values for K and gamma. So that's really good. Now you can, instead of using the absolute deviations, you can actually use the fractional deviations, and the fractional deviations, as I mentioned, is the difference divided by the measured squared. That will give you a different answer. If you do the same, it will give you a different answer, but close answer. It's not that far off, but it's slightly different. Because you're using a different minimization method. So yeah, so this is essentially how you use solver to do nonlinear regression type of work to find your parameters. Now, I believe one of your exam problems one of your homework problems deals with this, but it's not something that we are going to take you to tasks for. There's a chance you've done this before in a different way. Okay, so now let's essentially wrap up this section of this. It's one of those that has a lot of exercises, but really it can get complicated, but we decided not to make it so complicated. So if you wrap up, we've studied two different ways of analyzing your data to fit it to a rate expression. We have a differential method and an integral method. If we compare the two, what we'll find is that if we compare the differential method and the integral method. Now for each of these methods, there is a guide of how to use them, which I hope that I have talked about it, so that you can follow those and do your homework and understand how to do it. The one thing you find is that the differential method is inherently inaccurate, and I'll tell you why. The differential method is inherently inaccurate. And the reason is you're differentiating the data. And the way that we go about differentiate the data, we used a graphical method. We used a polynomial fit to differentiate the data from time versus concentration, or to time versus to concentration versus rate, those types of things. So in doing so, we introduce errors. But differential method is more flexible. And we saw that we can linearize the rate directly. Let's say for power law, we can determine the parameters directly, and we can find ways to linearize any rate expression to find out what to plot against what. So that's more flexible. The integral method is problematic if you can't integrate the rate expression. If you have a rate expression that is, let's say, something like this. And you do this in a batch reactor, or even in a differential, you do this in a differential packed bed reactor. It's hard to integrate this, so that's why using the differential method is more appropriate for something like this than it would be than the integral method. So the last 2 points I want to make here. The last 2 points is that, so use the differential method if the experiment actually gives you rate versus concentration. And yeah, and then if you can integrate your rate equation, your guessed rate equation, because once again we're looking at something we either guessed in one hand or derived from mechanism, and the mechanism can be wrong. So that means if you do your fitting and you find that your mechanism is not fitting correctly, then you have to hypothesize a different mechanism. So these are all things you need to keep in mind. So if you can integrate, use the integral method because that's going to be more accurate. And in both cases, you can linearize. And there was a case earlier when I linearized the rate for integral method, but you can also use nonlinear regression. And lastly, I'll just touch base on this. This is in the last section of the book, in chapter 6, some statistical methods to look at the fit. And these are things you can do pretty easily. For example, you can set up residual plots. Residual plots are essentially plots of concentration versus concentration that you've measured versus measured minus calculated. So you will get a plot. And if you have a good fit, so the plot will be across 0 because 0 would be there is no difference. So if you have your concentration that you've measured and then you have residuals, so if you have a good fit, it will be randomly around, your points will be randomly around 0. And of course, the spread should be really small. Say you have 0.2 minus 0.2 or something like that. So that would be a pretty good fit. However, if you have a residual plot that your 0 is here, but it looks like this, there's a trend somewhere or somehow, that means your actual rate expression you guessed is probably wrong because your data is not fitting. There's also something called a parity plot. A parity plot is essentially CA measured versus CA calculated, and that should be a straight line. That's what theoretically. But your data could be all over the place, and that would also be an indication that it's not fitting. So these are other ways you can look at your data after you've done your calculations to see if your data fits. One of the places where it's more appropriate, of course, if you have a power law, if you've done, if you've guessed a power law, it seems and if that's accurate, it should be easy. But if you have a reaction where you have something like this, this is a K. This is not just one K. This could be either. So let me see if I can get this right. Come on. This could be either, let's say, K1, K2, or it could be K1 large K2. You don't actually know what this could be. That's one of the places where things could go wrong. And you can have, say, a system like this. You can guess this, but it could actually be squared. So these would be the places where it's most appropriate to do residual plots and other sort of statistical analysis to look at your errors to make sure that things are what you think they are. And we talked about this before when we talked about surface reactions, that the square of squaring the denominator often means that you have a surface reaction that is dual site. for example, you can have a system where you don't know, let's say you have a system where A plus B goes to product, but you don't know, you know that A absorbed on the surface. So let's say A goes to the surface like this, but one of your guesses was B goes to the surface, just same way. However, it may be that B goes to the surface dissociatively, meaning that you have some BS2, so BS star plus BS star. So B dissociates and goes to the surface. But to make it easier to see, we'll do H, we'll do hydrogen dissociatively associating. So it would be hydrogen plus 2s, you'd have HS plus HS. So that's a different from having, that will be a different mechanism altogether. So you have two separate mechanisms. So that could be a source for your errors. So you have to always keep that in mind. So your exam will touch base on that. And that's kind of it's a nice way to bridge together mechanism and data. And one of your exam questions will basically be about looking at data and thinking about what your rating expression should look like and making some assessments or some comments about it. So that sort of closes our analysis of rates. And this is where essentially where the exam 2 covers and stops. So if you do the homework assigned, I know it was assigned a bit late and it looks like it's a lot, but it's not. Homework 5A is actually not much at all. It just requires you to do quite a bit of thinking, but it's not itself long. 5B is maybe a little bit longer, but it's just about plotting and understanding what you're plotting. So it should be straightforward to do. So let me say that I've made this part of the class as exciting as I could possibly do. I'm gonna go ahead and claim that's the case because now we're back to the fun. Like fun until the end. We're gonna talk about multiple reactions. That's it's gonna be as fun as it can. It can be brutal, so I have to say, because we have two. We're gonna teach this in two ways, so you can sort of appreciate both sides of it. There's a very quantitative side and there's a qualitative side. The qualitative side can be brutal for reasons of understanding concepts. The quantitative side can be brutal for reasons of tracking variables. Because the quantitative side, either you're going to use goal-seek in Excel, or you're going to use extent of reactions and two unknowns, or multiple equations, multiple unknowns, or you're going to use Python to solve. So that's like the quantitative side of it. The qualitative can be difficult just from understanding what things mean. So, and it doesn't let up from there, because right after that, we're going to go into energy balances, which now if you imagine having an energy balance with multiple reactions, then you have a multitude of equations to keep track of. But the way we do things in this class, you don't need to memorize anything. You just have to write things down in a very methodical way, and you should be okay. Okay, now that leads us to our next topic, which is design of reactors for multiple reactions. And I don't know how much of it I'm going to go through today, but what is the objective? So today we're going to do a couple of things. One objective is going to be we're going to introduce two terms: selectivity, yield. So these are two terms that we're going to define, and we're going to explain how they're related. The second thing we're gonna do today is to quickly classify systems of reactions. We might just do that first because it's actually the first thing it's probably the first thing we're gonna do. Then we are going to do a qualitative analysis of, we're gonna start with parallel reactions. I find they're easier to explain. And we're not gonna have time, but we're gonna think about the question, how do you maximize selectivity? So how do you do that? So most reactions don't have, most reactions in reactors involve multiple reactions, much reactors. So if you're gonna go through a process, they involve multiple reactors. And we may also, actually, rather than talking about maximize selectivity, we're not gonna get through that today, but we're gonna talk about reactor choice. Yeah, so this is, and how it's related to the reactions you want to run. This is really fun, reactor choice. Now, what kind of reactions do we deal with, right? I mean, we have, you can have a parallel reactions happening. So you can have parallel reactions where you have your A goes to B, but it also goes to C, right? Or you can have something like A plus B goes to C, and also A plus B goes to D. So these are parallel reactions. You can have series reactions. And we've looked at one of those before when we were talking about steady state approximation. That's essentially what that is. A goes to R goes to S. And then we can have a mixed reactions where it's something like, A plus B goes to R, but then R plus B goes to S. So there's a parallel reaction in there, but there's also series reaction. So it's parallel with respect to B, but it's in series with respect to R. So it's a mixed reaction. So the main thing we are considering is, how do we achieve a desired product distribution, and how do we maximize that desired product? So that is the goal of this chapter. Everything we're gonna do will be about maximizing the product that we wish to isolate. So I'll give you an example, industrial example of that is quite famous, which is olefin synthesis from naphtha. So yeah, so let's say you take ethylene and you want to make, let's say make ethane, you want to make ethylene. This is what you want to make. So you want to make this, and it's about 80 million pounds a year. That's how much is made of this per year. It's a lot. So, however, here's what actually also happens in your reactor. You also make acetylene. If you dehydrogenate too much, you can also do, I can never remember the actual term for this. I guess you can cleave the bond with hydrogen. There's a name for it. Can never remember. I need to look that up. The name for the process. You can also make benzene. And although this is a side product, there is a lab that I know of who found a way to turn this process and make it more selective for benzene instead of for ethylene, which is really cool. And you can also burn ethane so much that you end up making solid carbon. You basically make solid carbon, like dumping out of your gas phase reaction. So this is essentially something that's industrially relevant, and often you want to make ethylene. So the question is always, how do you maximize ethylene production. And a lot of things goes through this, including catalyst choice and design. But here we're gonna talk about reactor design isothermally, because we're not gonna be messing too much with temperature changes and activation energies, and we will talk mostly isothermal. Okay, so we are going to define two things. Oh, sorry, we're gonna define two things. The first thing we're defining is yield. So yield, let's first say you have a reaction that is A goes to B, and there's a second parallel reaction, A goes to C. Okay. If you have that, the yield is gonna be moles of B formed divided by moles of A fed. So this is your yield. And you also have to multiply by stoichiometric coefficient. So the numerator is multiplied by the minus nu A, and the denominator is multiplied by nu B. This is how you keep the stoichiometry. So basically, if you have a batch reactor, it would be something like Na NB minus NB naught over Na naught. So this number will be positive because minus nu A is positive. So yeah, essentially. So that would be a batch reactor sort of yield. And for flow reactors, same thing. You would just replace N's with F's. And this is what yield is. That's pretty straightforward. The more complicated, however, is selectivity, because it can be defined in many ways. So that's a bit more complicated. I need to figure out how to ever understand why this happens. All right, anyway. So you have selectivity, we'll call that S. This is the yield of B with respect to A. Okay, that's the selectivity of B with respect to A. It's the moles of B. One definition we're gonna go for now is moles of B formed times minus nu A over moles of A reacted. Okay, so this is the definition for selectivity, one of the two that we're going to talk about. So that's the first thing I wanted to say. So let's say it would be NB minus NB naught times minus nu A over NA naught minus NA times nu B. Okay, so moles of A reacted. So everything is positive. Right. So if you were to make a mistake and you switch Na minus Na naught, then it will be a negative number. Then you'll find out, because you can't have a selectivity. This selectivity goes from 0 to 1. Right. So it's a fraction. So it goes from 0 to 1. So, and then, with flows, we just replace N with F. So we have selectivity. This is what you call this an overall selectivity. And we'll talk about in a minute the difference between that and another type of selectivity. This is overall selectivity. This is after the reaction is over. And in a minute, we'll talk about some other type of selectivity. Now, the relationship between selectivity and yield is if you divide Y by S, so B with respect to A, I just omitted those. This is B with respect to A for both. If you divide through, you find that this is equal to Na naught minus Na over Na naught, which is equal to XA.
Dr. Denard,
Yes.
for the equations, is NB minus NB naught, is that supposed to be in parentheses, both multiplied by the new A?
Yeah, they're both multiplied by new A. So let me correct that. Yeah, it's the same thing here. Ah. Yeah. All right, so yeah, so the relationship between yield and selectivity is the conversion. Now, the other thing I wanted to add is in solving these problems, we are not going to use fractional conversion a lot, even though I just said it's the conversion is relationship, but we are actually not going to use fractional conversion a lot, and I can show you why. Let's say you have, a reaction of methanol being oxidized to an aldehyde, and then that aldehyde goes on and reacts with oxygen again to make carbon monoxide and water. So if I ask you the final concentrations of the aldehyde, you can't use fractional conversion because it never showed up as a reactant. So the N naught of CH2O is 0, so the yield will be dividing by 0, so that would give you an error. So we'll be using extent of reactions, so for reaction 1 and reaction 2, and we'll also be using concentrations. So, C of methanol or concentration of the aldehyde and stuff like that. Okay, so that's what we're going to be using to solve those problems rather than fractional conversion, because that would can lead to some problems. It's just as a precaution. So that leads us to our first example. So we're going to do a few examples over the last few lectures until the very end. It's going to be really example focused, so that you can see. There's going to be a few less theory. There's going to be much more examples. So let's do example. Let's call it example 1. This deals with the relationship while calculating selectivity, and also talking about the relationship between selectivity and yield. So we're going to do 2 examples. And these examples are things that you should think of for quizzes, because they're really simple and they're really simple to ask questions of. So you should think of those. So consider this reaction of 2A goes to B and A goes to C. Okay, and then this is happening in a batch reactor where initially there is 10 moles of A. So that's what you have, and there is no moles of B and no moles of C. And you're told that eta1 is 3 moles and eta2 is 2 moles. So these are your extent of reactions for 1 and 2. Now we're going back to chapter 1. So remember that eta1 for the first reaction is Na1 minus Na0 over nu A1. And it's also equal to NB first reaction minus NB0 over mu B1. And that's equal to 3. Okay, so we can say that Na1 minus Na0 is equal to minus 6. And then NB1 minus NB0 is equal to 3. Right? So we can say that. So we can do the similar thing with the second extent of reaction, because now it's Na2 minus Na0 over mu A2. That's the only place where it appears, so we only do that one, and we can compute that Na2 minus Na0 equals 2, minus 2, sorry. So one of the examples in the book, I believe example 7.1, you should look at that. Does a more extensive job of looking at what's the mole fraction of its species in a system with multiple reactions. So you should look at that for sure. Now, if you're looking at selectivity of B with respect to A, so this is what we are asked. Respect to A. So S of B over A. What it's equal to is moles of B formed. And I'm going to throw a little wrinkle here. So moles of B formed, so that's 2, right? Because there's NB naught is equal to 0. Oh, that's 3, sorry. That's 3, so that's moles of B formed. Let me write it down instead, just to make sure. So it's moles of B formed times minus nu A. And this is where B is formed. Reaction in which B is formed. So that's the only wrinkle you have to keep in mind. So that minus nu A is going to be 2, right? That's the place where B is formed. Okay. If B is formed in multiple other reactions, then we have to multiply it by the reaction in which B is formed. Okay, so then moles of A reacted, and the new B, it's been in the first reaction, it's 1. Now you can see the problem can be that if you have a much more complex set of reactions, so the way you're going to define selectivity can be different. It may not be easy to define this. Let's say B is being formed in many places, sometimes not even with respect to A, but not directly with respect to A. Let's say it's another way. Let's say you had a thing where this happened for some reason. For whatever reason, let's say this happened. So the selectivity here would be complicated to calculate with respect to A, but there is other ways you can define selectivity to account for these sorts of things. But for this class, we're gonna keep it simple, and we're gonna try and, I guess I didn't mean to put it in red. We're gonna try and keep it simple. Okay. All right. So what this is equal to? So moles of B formed. This is nu 2. This is nu 1. Right. That's 3 moles times 2. Okay, and that's divided by moles of A reacted. That's E1 plus E2, I believe. Is that correct? Moles of A reacted is 2 times E1, sorry, 2 times E1 plus E2. So that's 6 plus 2, that's 8. So 8 times 1, because we've calculated that here. So oh, I already did. What am I saying? Anyway, so 8 moles of B, 8 moles of A has reacted. So there's 6 goes in the first reaction, and 2 went in the second. So you've got 8 moles. So your selectivity is 3/4. So you have to keep in mind. Yep. Question?
Can you explain where the 6 and the 2 come from again?
Yeah. So in the first reaction, if you look at your eta 1 means that Na1 minus Na is 6. So 6 moles of A reacted in the first reaction.
Okay.
Right. And in the second reaction, here, eta 2 is 2. And if you look at again your law of definite proportions, it tells you that 2 moles of A reacted in the second one. And then 2 minus that naught. So that's where your 8 comes from. This is moles of A reacted, completely reacted. So you get 3/4 for your selectivity. Now you can check something here. You can say, what if all of A went to B? So no A went to C. So what if all A went to B? If all A went to form B, you would form 5 moles of B. Because the reaction is 2A goes to B. So you would form 5 moles of B from 10 moles of A. Okay. And then if you were to look at selectivity, it should be equal to 1 because it would be 5, okay, times 2, which is the stoichiometric coefficient for A, over 10 moles of A that has reacted because all of it reacted. So you start, because remember you started with 10 moles of A, and that should give you 1. So you can always double check yourself when if you have a problem like this. Yeah, the only thing to keep in mind is, it can be a little tricky when you're thinking of what reaction is forming B. Now, this is a simple example, but there could be one that can be a little tricky, but I don't think you'll see it in this course because this is only really as an example. Now, here is the kind of problems you'll see. If I'm being completely honest here, the kind of problem you'll see will be, let's say, second example is taking advantage of the relationship between yield, selectivity, and conversion. The second example is about relating yield and selectivity. Okay, so let's say you have a parallel reaction, A goes to P and A goes to W. You're told that the overall selectivity, and here we use the word overall selectivity because there is another one called point selectivity, which we'll talk about soon. So the overall selectivity of P with respect to W is 4. So what this is SP with respect to W. And this is another way of looking at selectivity. What it is moles of P formed times nu W over moles of W formed times nu P. So this is another way you can look at product selectivity, right? Because let's say P is your desired product, W is your undesired product, so you can look at the selectivity that way as well. So that's what I meant by there's many ways you can define it. I'm just telling you about 2 of them. There are probably 3 or 4 different ways you can define selectivity depending on what your reaction system is. And often if you look in the literature, they will define the selectivity before they tell you what it is. So because it's subjective, you have to just say what it is. So let me see. Now, this selectivity can be higher than 1 this way. It cannot be higher than 1 when it's respect to reactants, but it can be higher than 1 if it's with respect to another product in your reaction. So if they tell you're told that the overall selectivity of P with respect to W is 4, and you're asked what is the overall yield of P with respect to W. Okay, or with respect to A, what am I saying? Respect to A, if NA equals 0 at time 0, at time T. So,
Dr. Narn, I had a quick
Mhm.
question. So you're saying the only case where like selectivity can be higher than 1 is if it's a product respect to a reactant?
no, if it can be higher than 1 if you're relating 2 products.
Oh, okay, 2 products.
Yeah, 2 products.
In every other case, it'd be between 0 and 1.
Yeah, well, if it's related to a reactant, it's between 0 and 1.
Okay.
I'm not gonna go as far as saying it's every other case. I think that might be too broad. So
Got it.
yeah, with respect to reactant, it's between 0 and 1. If it's between two products or intermediates, right? It could be higher than 1.
Got it. Thanks.
Okay. So you're asking the question, what is the overall yield of P with respect to A if at the end of the reaction there is no more A? So the way you solve this is you first write out the selectivity of P with respect to W. And that you tell you it's 4. So this is moles of P that is formed. So it's NP minus NP naught times the stoichiometric coefficient of W, and that's 1 over NW minus NW naught equals that. Okay. Now you should notice this, even if you were, so to, sanity check, you could do that. Because remember, that's what we did for A. This is a P. It's the same thing. You just have negative signs that are being flipped in and out. So it's the same. So I switch NW naught minus IW for that, and the negative sign goes away. So it's the same thing. So in case you could get slightly confused, but it's fine. It will all give you a positive number. Okay. Just making sure. So if you do this, and you will find that, so NP naught is 0, NW naught is 0, and then this is 1 and this is 1. So that tells you that NP is equal to 4 times NW. So that's what this means. And if you were now to look at yield of P with respect to A, and that's what you're being asked to calculate. So it's NP over NA naught. Okay, so it's NP over NA naught. So you could do the same, minus new A, new P, but these are 1, 1, right? And that tells you that, so you're at NP, so NA naught is gonna be NP plus NW plus NA. So basically conserving moles. So the number of P and NA naught became PW and whatever is left of A. So this is 0. So you're told that is 0. So you can replace NW with 1/4 NP, because NP is 4 NW, and that should give you 4/5 for your yield with respect to A. So these are the sort of questions you could be asked on quizzes, because they're pretty simple. Couple of different relationships. So you could see the conversion being thrown in there as one of the ways to relate the yield and selectivity. So conversion could be thrown in there. You could be told that at 75% conversion, the yield is certain amount. What is selectivity? So you could use the same relationships to compute these sorts of things.
I have a quick question. So how come you can plug in NP plus NW plus NA for NA naught?
Because NA is the only thing being fed. It is being reacted to form NP and NW.
Oh, I see. So the NA naught becomes all of those three things.
Yeah, it becomes all these three things.
Okay, thank you.
Yeah. Okay, so yeah, these are a couple of examples. Before we move into reactors and more complicated systems, we can look at simple relationships between, and example 7.1 in the book does a pretty good job at that as well, so you should check that out. But I think I wanted to show simpler, more straightforward, quick and easy ones to work through. Okay, so where are we now? Okay. Now we are at the last little bit of Cool.
Dr. Denard,
Yes.
do you mind if we take a quick 5-minute break?
Actually, yes, I forgot. Yes, go
Nice.
for it. I completely forgot. Someone should remind me because I sometimes forget to do that. All right, I'll pause the recording, but that's okay. All right, so we are careful of mentioning overall selectivity every time because there is another selectivity called point selectivity. And now we're going to talk about that. And this is where the fun really, really kicks in. At least from a qualitative point of view. Instantaneous versus point versus overall. Because it's instantaneous is point versus overall. Sorry. Selectivity. We'll call selectivity overall, we'll call S, and instantaneous we'll call S hat. Okay, just for our own differentiations. I don't think it's called that way in the book, but just making sure we can differentiate that. Now, I'm not gonna write, I'm just gonna explain this. So if you have a batch reactor with multiple reactions happening in it, you have multiple reactions happening, or you have a PFR with multiple reactions happening as the reactants go down the line, go down the reactor. Since the selectivity, right, is, let's say, of selectivity of one over something over another is mole formed, for example, per mole reacted. So this selectivity is going to change. The selectivity is going to change as either time passes or the reactants go through the PFR, right? The selectivity is going to be something at the beginning and it's going to end at something else. So the point selectivity or instantaneous selectivity, say you have a simple reaction of A goes to B or A goes to C. Say if you look at the instantaneous selectivity of B over A is actually equal to RB, the rate of B, over the rate of A, and we can do something like this. Okay, so this is instantaneous selectivity. So at every instant, the selectivity is changing, or point selectivity at every point is changing. It could be time point or space-time point. Okay, that's instantaneous. That applies for PFR, PBR, right? Packed bed as well. But now if you look at a CSTR, where the idea is that it's so well mixed that as soon as the reactants enter, they are at the final concentrations. So for a CSTR, and this is different from S overall, right? This first case for PFR and batches is different. But for CSTR, it is the same, because as soon as the reactants enter, they have achieved their final concentrations. So that means whatever the selectivity is, it's the same throughout the entire reactor. So that's the key that you need to remember here. Any questions? Does that make sense? Okay. I don't see any thumbs up or anything, but I'm going to assume that there are thumbs up because it's pretty straightforward, right? It's that's the basis of basically most of our qualitative assessments. That's pretty much it. You can derive it mathematically. There's really no need. You can just understand this is what's happening. And this is the last definition that allows us to now start talking about what are we doing. So we did a quick little detour and looked at how we relate selectivity and yield. This is just, little, small exercises to understand terms. That's really what it means. And for example, in an exam, you could be asked, what is the selectivity? You have a reactor, you design it, you size it, you have volume, you have your concentrations, and the question that you ask is, what is selectivity of your product, over a reactant fed? So you use some of these relationships we derive at the beginning to compute that. So that's the goal. Right now, what are we actually doing from the point of reactor design? So this is the question that we ask. So the goals really is two of them. Maximize reaction rate, which goes hand in hand with minimize reactor volume. This is similar to what we did from chapters 2 through 4, right? Looking at how can we put the smallest reactor to give us the best rate, the best yields, the best conversion, or something like that. And the second thing we're doing is maximize selectivity. That's what this chapter is really about. And that complicates things because now you have to make trade-offs. Selectivity versus yield, selectivity versus rate, selectivity versus conversion. So you have to make those trade-offs. So you ask yourself a few questions. One question is, what kind of reactor or systems of reactor can I use depending on what my reaction system looks like? Can I use a CSTR? Does that help or hurt selectivity? Can I use a PFR? Can I use a system of continuous reactors, a batch? Can I use a semi-batch? What type of reactor will give me the best result? So that's the question. And what concentration of feed do I do? Do I have a high concentration of feed, low concentration of feed? Do I feed one of the reactants at different intervals or slower? And what temperature should I use? Should I operate at a high temperature or lower temperature? Although we're operating isothermally, but do I have the reaction set at a high temperature, or the reactor set at a high temperature or low temperature? And okay, now this is sort of the questions we asked. There was a lot to write down, so I decided not to. Now, what I'm gonna write down, however, is the method for, or as Fogler calls it, the algorithm for solving problems involving multiple reactions. It's also in your book, but it's in a big paragraph, so I just sort of succinctly put it together. First thing you do is you have to have a rate equation for each independent species. So you need independent reaction, not species. Sorry. For independent reaction. The second thing you need, so this is A, B, you need a mole balance on each independent reaction. I guess it would be, that's where species comes in. Sorry, each independent species. That's what I meant. And C, you need an independent composition variable. What that means, you need eta or concentration. So composition variable for each reaction, or for each reaction. So it could be eta, right? So if you know eta I, it could be eta 1, eta 2, eta 3. For each reaction has a different extent of reaction. Or we can use concentrations, and we're gonna do that too, to solve that's when we sometimes that would be when we use Python, for example. So we can use concentrations, and you'll see that it's gonna be fine. So this is the method, right? So then, what kind of problems are you actually gonna be asked to solve? One problem is very similar to what we did before, is calculate. So problems to be solved. One of them could be, calculate reaction time, calculate reactor volume. So these are very similar. Reactor volume. You can also calculate well, that's a second point. You can also calculate selectivity, yield. The third thing, you can be asked to recommend best reactor, and you need calculation to show that. This is another type of problem, best reactor or systems of reactors for your equation. And you could also be asked to do time or space-time independent analyses, time or space-time independent analyses. Or even reactor independent analyses, but it's not the right way to say it. But so time independent analysis, that means that you're dealing with concentrations only. You're not dealing with the volume of the reactor. You're not dealing with the time it requires for certain selectivity to be reached. You're not dealing with that. You're just dealing with time independent. And then we're going to talk about that in just a moment, what that means. That means when you relate concentrations in terms of the point selectivity. So we're going to take advantage of the point selectivity to look at our systems of reactions. Okay, so now that I've, there's a lot of, we spoke a lot about what we're gonna do, and then maybe a little bit of how we're gonna do it, but there's no better way to learn than to just do it. So what's the approach that we're gonna take? We're gonna take two approaches in this section. There is a more qualitative approach, understanding a little bit more about how systems of reactions are related and how we can understand information from them. And there's a more quantitative system where we go and solve for parameters, go and solve for variables, and we get things like selectivity, we get things like reactor volume, we get other types of things like that, and I show you how to use GoalSeek, Solver, Python to solve for these sorts of things. But there is also the qualitative aspect, which is also if also important, if not sometimes more important. So rather than starting with reactions in series, which are fine, the fun is in reactions in parallel. Reactions in series are fine. There's nothing to write home about. Let's talk about reactions in parallel. So and of course, we'll eventually talk about mixed, parallel and in series at the same time. So let's look at a qualitative approach. So we're not going to put any numbers in. Let's say you have two reactions. A goes to D, and this is desired. That's why we call it D. And its rate, RD, is KDCA alpha 1. So power law. And then we have another reaction where A goes to U. This is undesired with KU. So our plan is to make D and not make U. So RU is just KU CA alpha 2. So these are the reactions. We're not dealing with reactors yet. We're just looking at the reactions themselves. And yeah, so we're asked to, can we maximize the selectivity of D with respect to U? So that's what we're asked. So, but we don't have any molar flow rates or anything like that, okay? It's just telling you, how do you maximize the selectivity of D with respect to U? So what you do is you write it out. So S hat, this is your instantaneous selectivity of D with respect to U. I'm gonna show you two ways that we can do this problem. The first way is the following, RD over RU. Now I omitted the new D and new U because they're equal to 1, okay? And this is equal to KD over KU CA alpha 1 minus alpha 2, right? It's just dividing those two by, dividing them by one another. Okay. So the first thing you can ask yourself, well, what if, so we'll do case number 1. What if alpha 1 is more than alpha 2? And you can say that alpha 1 minus alpha 2 is some positive integer. So this is a positive number. Okay. Let's say alpha 1 is higher than alpha 2. In that case, your instantaneous D over U is KD over KU CA to the A to the power of A. So what you can say here is that the question you ask is, how do you maximize the production of D? So the question is, I'm going to write those down. So that it could be in terms of reactor type, temperature, and something that found in other books. It's a nice way of saying, how do you feed things? Contacting pattern, feed concentration. So these are the things that you are looking at. You're like, which one do I pick to run my reaction? Under what conditions do I run my reaction? So now, oh, wait, see, this happened again.
Wait, what does contacting pattern mean?
Contacting pattern means how do you feed things? But we'll get to that. So for example, if you have two reactants, do you add them at the same time? Do you add one before the other? Do you add one at a high concentration, the other one at a lower concentration? That's what contacting pattern means. It's a fancy word of just saying, how do you feed the things? Let me see if I can fix my computer is giving me trouble. I don't know what's up with that. Okay. I think I should have changed it. I should not change the color of my pen. Whenever I do, it gives me problems. Okay. All right. So what you notice here is that to maximize this, so remember A is a positive integer, you have to carry out the reactions in a manner that will keep the concentration of A as high as possible. So that's what you have to do. So if you want S to be highest, you have to keep the concentration of A as high as possible if you want SD over U to be highest. Any questions about this before I continue? What I'm trying to say? Okay, we'll get to case number 2 and then you'll get it as well. So And you remember from chapters 3 and 4, I think it was 4, to keep the concentration of A as high as possible, or the pressure, the partial pressure, that's the same thing. Of A as high as possible, you use a PFR. So what you do is you use PFR or PBR. You don't have any inert, or if it's liquid phase, no DUI. So that's the idea. So if the order of your reaction that you desire is higher than the one that you don't want, you keep the concentrations as high as possible, because the as high as possible, and you don't dilute things. You keep things at high concentration, and you run it in a packed bed reactor or a plug flow reactor, so that the concentration is always maximized. Because if you run it in a CSTR, the concentration is evaluated at the outlet concentration, which in this case would not be the highest that it can be. So that's essentially one qualitatively what you do when you have multiple reactions. So you can look at case number 2. Let's say now alpha 1 is less than alpha 2. So your desired product, the order of that rate expression is lower than the undesired product. Say now you have alpha 1 minus alpha 2 equals B, some constant B. So you can write SD over U is equal to KD over KU CAB, because now B is a negative number. So you can write it that way, right? Or you can write CA minus B, or well, yeah.
So are we talking about S or S hat?
S hat.
Oh, okay.
Yeah, I think that's what I said. Oh, yeah, I just forgot that hat now, right? I didn't forget it before. Okay, got it. Okay. Because I could forget it sometimes. Yeah, I could forget it sometimes.
Yeah.
So in this case, it's the opposite, right? So to maximize S hat, you have to carry out this reaction in a way that keeps CA as low as possible. So let me see if I didn't skip something. Let's make sure. Oh, looks like I did not. Okay, that's good. Okay. So yeah, so the idea is to now keep CA as low as possible, meaning you use a CSTR and you add inerts or dilute it. So this is how you would run that reaction. So for example, if you had a reaction where, if you had a system where, right, so that RD is KCA to the 1/2, and RU, let's see, KD, KU, CA to the power of 2. So at high concentrations, you'll form more U than D. That's what this means. So the best thing you can do is to run this reaction as low concentration of A as possible, so that you don't favor U. It's still challenging to run this reaction to have high selectivity for U, for D over U, but you'll get better selectivity if you run it at low concentrations of CA. Now, the third kind of qualitative idea is related to the rate constants. So let's say now, once again, you have this. You can write it as, oh, made a mistake. You can say that, okay, well, you can say, okay, so it's KD over KU, right? Because that's one thing that's part of the equation. So it's the pre-exponential factor AD over AU times e to the minus ED minus EU over RT. So this is how you relate the two activation energies. So now you can start talking about temperature. So what temperature would you run the reaction depending on what the activation energies are, right? So you can basically write it this way. For example, you can have a case if the activation energy of your desired reaction is higher than the one of your undesired reaction, then the question, what you would do is to operate at highest possible temperature. Because this is S hat, and this is with ED more than EU. And this is temperature in Kelvin, meaning that with increasing temperature, the rate of the desired reaction goes faster because K is higher for the desired reaction than it is for the undesired reaction at high temperatures. So you can be selective for the desired reaction. And we have a case number 4. So we have actually 5 cases, even maybe more than that. So let's say we have a case where now you have the reverse. So what that means is that your selectivity S hat is going down as temperature goes up. If you have this happening, then it's to operate at the lowest possible temperature. But not too low, because if you operate at too low temperature, the reaction will not go forward. So this is what I mean by a big trade-off. So if you have to operate at a low temperature, but if it's too low temperature, the reaction is not going to go anywhere. So you want to have a temperature that is appropriate. Now the last case here is if you have, and this is even more interesting here, if you have then this system. So you have A plus B goes to D and A plus B goes to U. That's in the book. So you have, let's say, RD is KD, CA alpha 1, CB beta 1, and RU is KU, CA alpha 2, CB beta 2. So you have these rate expressions. Now, the instantaneous selectivity here is KD over KU, CA alpha D minus alpha U, or I guess I wanted to say did I make a alpha 1 over minus alpha 2? That's what I meant to say. And CB make sure before I make a mistake. Oh, I see. I apologize. I know where I confused myself a bit with the subscripts. There we go. There we go. That makes more sense. All right. So you can write it this way. And now if alpha D is more than alpha U and beta D is more than beta U, then is to keep both species at high concentrations. Because both of them being at high concentrations would mean that you're getting more of your desired product because the desired product order is higher for both species. However, if you have alpha D more than alpha U and beta D less than beta U, you have to keep A or PA high, but keep B or PB low. So this is where the fun starts. And this is the last thing I'll mention here before we take off. So one way you can do this is using a semi-batch reactor. And this is where what we're gonna do next time. So this is you feeding B slowly, and the batch reactor, the semi-batch reactor has A initially. So that way you're keeping B at a low concentration, because every time B gets added, some of it, a lot of it reacts. So this is a semi-batch system. You can have a system that we will not be solving. It's a tubular reactor with side streams. So this is D and U coming out. This is A. This is B, but before it goes in, you're putting it at different sections along the reactor. So the assumption is that this is a PFR or PBR. Right, this is this reactor there. The assumption is as you move along in the reactor, you're reacting. And every time you get to a point, you get some more B getting fed in. So this is another type of reactor that you could say that you could solve. There's a problem in the book actually that talks about solving different reactor portions. You could solve the first quarter, the second, the half, the 3/4, and the full. You can find out what the conversion is in each as you move along the reactor. There's a problem in, I think, chapter 4 that deals with that. Or you can have a series of CSTRs, small CSTRs. So small CSTRs, not large ones, where B is fed in small amounts. So you can have a system like, so I'm gonna draw it like this. So you have A goes into one CSTR. You have B coming in. And then some comes out, goes into the next CSTR. And some more B is coming in. And you go into the third CSTR and more B comes in. I guess I should have drawn it this way instead. Yeah, so you can have those kinds of systems. So that's why I wanted to talk about parallel reactions first. Series reactions are also fun to look at, but parallel reaction gives you lots of cool options. And when we get to solving problems, we look at parallel reactions and solve problems where we know we're going to do a semi-batch, and we'll do Python and look at how things are moving with semi-batch. And so that will stop now. So what we'll talk about next class. So next class, I will teach in the first 45 minutes to finish up parallel reactions, just to make sure that we've wrapped that up so that you can do either some homework, and you can more or less have a full picture of parallel reactions. And then we'll have about an hour or so of review. And I will say that, but if I'm being frank, to be frank with you, oops, there we go. All right. So to be frank with you, I only really have 1 or 2 past exams that look or that could be used to prepare for this exam you're getting next Thursday. Because I have decided to write a very, very different exam. It's not harder or easier, it's just a different exam. And I would tell you that the homeworks that we did and the surface reactions, that becomes, the Romana, it only stops after, nonlinear regression. So that's where we stop. So it's going to cover, recycle reactor, pressure drop, impact bed reactors. And it's going to cover surface reaction mechanisms, surface reactions, and an analysis of data and figuring out your reaction orders based on data. I'd ask Alex, Jess to prepare a few additional examples that he will either work out with you or post so that you can have a better idea of what to expect. Because the exam will be many more problems than 4. So it would be, let's say, 7 or 8 smaller problems. One of them could be big, but like smaller things that allow you to, because there's a lot of topics. So we'll be able to test all the topics.
So quick question, you're saying that basically the format is going to change?
Yeah, it's not going to be 4 problems or 3 problems. How many problems were this the first time? I think 4 problems, maybe 3. I think it was 3. Yeah, the format is going to change. It's going to be double that. Yeah, but it's going to be shorter problems, smaller problems. Maybe the problems may not have as much algebra, because let's say it's a problem about looking at data and trying to think, how does the data, can help you figure out what your rate expression is. And I think we have a homework on this, right? There's not much, there isn't much math, right? It's just thinking about it and maybe draw out some curves and some plots and think about what they look like. So that's why there will be many more problems, but they, one can go through each problem every 10 minutes or something like that. So that's the idea. So that's what we're gonna try and do. So I'm gonna try and send some past exams this afternoon or tomorrow morning, and Jess is I've already spoken to him about coming up with a few examples to sort of guide you through. But honestly, I don't think you will need all of that, but I'm sure providing it in case things don't go as planned. So I imagine you won't need all of this, but make sure you do the homework. Make sure you look at the homework solutions. Those are important if you didn't do the homework, because I know only 29 of you did out of 40. So make sure you do the homework, because it's gonna come and bite you in the butt. So yeah, the homework does matter. So yeah, so with that, we'll meet up next Tuesday for an hour, and then Jess is gonna take over for the rest, and I'm gonna ask him to have an office hours before the exam, because I think he usually has them Thursdays and Fridays or something like that. I'm gonna ask him to have one either Monday or Wednesday, so that you guys can come in and ask more questions if you don't have a chance to ask them in my office hours next Monday. I'm also having office hours tomorrow afternoon at 4. So like I said, I'm providing all of this. I don't think you'll need it, but make sure that it's there for you so you can take advantage of it. That's the idea. So bring questions about the homework, because you just got assigned the homework. So bring some questions. Make sure you can understand things. I'll be happy. Some of you have been at office hours. I'll be happy to go over the notes again. That's what I've sometimes done. So yeah, make sure you show up. I always tell people, you all start with an A, you just mess it up eventually. So you'll be fine. All right, guys, I've kept you long enough. You guys have a good one.
Thanks.
Mhm.